Okay, so let's get on with our program. We've got a pretty exciting talk coming up next, Monsters on the Move. I really like that title. Yashashree Jadhav actually came to this room back in the fall when we hosted our technical conference where students and researchers share their results, and she gave a much shorter version of the talk about her research, and we thought that's pretty cool. And I think actually Ken Steiner probably was impressed by it as well, because I see she's on the Southern Star list as well, where she will give more talks than just this one. There's a lot of exciting astronomy going on over at Elon University, where she is teaching there this year. And so I'm going to turn things over to her and let her tell us about recoiling black holes.
Thank you so much. So I hope you've all had a wonderful lunch and there isn't a monster in your stomachs anymore, but we will be talking about other kind of monsters today. And whenever I think about astronomy, whenever I think about active galactic nuclei, supermassive black holes, I like to think of them as monsters. Maybe little ones with their eye. Do we recognize which monster this might be? Maybe this might help. And one of the reasons why I like to think of black holes as monsters is related to how we perceive of black holes, especially in media, in movies, in even television series, like this one. Now, this is one that I think most of you have probably seen in a very popular movie, Interstellar. Interstellar was one that came up with a black hole. Now, this is a smaller black hole, not a supermassive, but pretty remarkable nevertheless. This one is a stellar mass black hole, and it has that little planet that's going around it. I think it had a couple other planets going around it, some wonderful things that they did with it. And why I find this particular black hole especially remarkable is because of what happens when you give Hollywood a couple $1 billion in budget. And we get this. We get an actual model of a black hole that they tried to create. They wrote a paper about it, which is fun to read. So go and do that if you want. But that's another one, stellar mass black hole that we have. Let's see what else we have in media. We have devoured by gravity. We have gravity that's distorting everything. And that's absolutely something that black holes do. But I love this perception of how we view this enormous thing out in space that is eating everything that's coming towards it and thinking about objects being sucked into a black hole, which honestly isn't a term that I'm particularly fond of, because it's more like an in spiral that goes in and in and in, and finally you go inside. But now let's take a look at what scientists have done with how we see, or how we think we will see, black holes. And of course, we go back to our computers and we do our little simulations and we come up with something that looks like this. So this here is a computer simulation of what a black hole looks like. And now there's something interesting happening about here, which is actually similar to Gargantuan, the black hole in Interstellar, in that we don't just see a disk, but because of distortion, we also see something going around the black hole. Now, what I want you all to do is keep looking at this. Some of you know where I'm going with this. Keep looking at this. And now I'll come to two images. These are not simulations anymore. These are actual images that were taken by the Event Horizon Telescope of two different supermassive black holes. So the one on your right, my left, your right, is Sagittarius A star. That is our black hole. In the Milky Way, our galaxy, that is what's at the center of our galaxy. And the one on your left here, M87, that's another remarkable galaxy which many of you are probably familiar with as a Messier object, M87. That's M87's black hole at the center of that galaxy. Let me do a quick back and forth. So we have our simulation and reality. Back to the simulation, back to reality. Very similar, aren't they? Both of these, very similar concepts between what we thought we think a black hole will look like and what we really see a black hole looking like. But now the question is, this is a supermassive black hole at the center of our galaxy and at the center of a different galaxy. How big are they? How big, how massive, both in terms of mass and in terms of size, are these two black holes? And when we look at these, they look comparable, right? Like when you just see these two images, they look comparable. But are they comparable in terms of size? Now, here's an example of different parts of a black hole. You have the black hole at the center, you have the event horizon. If you go beyond the event horizon, yeah, we're never hearing from you again. That's it, that's it. No light is coming out of there again. But you have the emission ring, you have other parts of the black hole. This is my favorite part. When you compare the black hole that's at the center of our galaxy compared to the one that's at M87, yeah, look at the size scale. We have Mercury's diameter there, Mercury's orbit. That's the size of the picture on your right. One on the left, that's a pixel. One tiny pixel at the center of that black hole. Sagittarius A star is about 1,000 times smaller than this one. That one is several million times the mass of our sun. This one is about 5.4 billion times the mass of our sun. And just take a second to sink that in, how massive this object is. Both of these are supermassive black holes. Both of these are the centers of galaxies. But one of them is 1,000 times larger than the other. And here is where our story begins. How does this happen? What causes a black hole to go from only, little tiny million times the mass of our sun to billion times the mass of our sun? And what we have is, we start with this. We start with, there is a supermassive black hole at the centers of pretty much all large galaxies in the universe. But what happens is, just like our galaxy is going to one day collide with Andromeda galaxy, galaxy mergers happen everywhere in the universe. So we have this. With galaxy mergers, galaxies are merging everywhere in the universe, and that is how these black holes are going to grow. Because once these galaxies merge, in a term which I like to very dearly call mutual cannibalism of galaxies. So mutually cannibalizing each other, we have the two central supermassive black holes. Come together, then they start going around each other. Eventually, they're going to merge, but first, they come together, they start going around each other, and we have evidence for that. Earlier last year, this pair was confirmed. This is a dual AGN pair. This is a pair of two supermassive black holes that have been found at the center of this particular galaxy at about a couple hundred parsecs away from each other. Eventually, they are going to merge. But before I even get into that, I wanted to take a step back and look at this picture here. This picture, in fact, is not even a picture. This is an artist's rendition. This is not a real picture. And I'm sure a lot of you will see this and will immediately know this is not a real picture. Because to get a real picture, we have to look at one of these. This is our beloved electromagnetic spectrum. Visual is mostly what we all see in. Unfortunately, unlike birds, we don't have windows apart from the visual. But we do have other things. We have telescopes. We have Hubble Space Telescope, which has visual windows. We have James Webb. We have Spitzer. There are only 3 here, but there are so many other telescopes that we use to look at the universe, to look at the different bands in which we can get data from the different parts of the electromagnetic spectrum. Like this one. This here is the Horsehead Nebula. It's a wonderful photo. And for the longest time, this was it. This was the best resolution that you could get with the Horsehead Nebula. This picture was taken by the Hubble Space Telescope. Well, a couple years ago, we had another one go up. We had James Webb go up. And because of James Webb Space Telescope, we now have this. So I'm going to do a little back and forth again between the two images. So visual versus infrared. Getting those two windows, you can have visual, infrared, visual, infrared. Collection of 4 stars to your right there, that was not visible in visual, but it was in infrared. So once we expand the way we are looking at the universe, a lot more things start coming out, which is exactly what we did. So this one, who knows the Messier number for this one? M1, wonderful. So M1, this here is a composite of a bunch of different images taken in a bunch of different wavelengths. Start with radio, you go into all of the other different wavelengths that we have in that one particular picture. You put that together and then you get a complete picture of what M1, or your little crab nebula, looks like. All the way down to X-ray, all the way down to its most energetic parts. So all of these images put together, you get Crab Nebula. One more. There's NGC 1566, or Spanish Dancer Galaxy. Here, there are 3 of them. I have UV, I have HST Invisible. Try to turn it to fit the James Webb as well. This was an astronomy picture of the day a few weeks ago, I want to say. But again, when you start looking beyond what's just visible in front of you, like the UV or the infrared or X-ray or radio, you start seeing a lot more of the universe. But where am I going with this? This is the electromagnetic spectrum. If anyone's seen Avatar, I really like the phrase when they say, everything changed when the Fire Nation attacked. And I'm going to use that for gravitational waves. Electromagnetic spectrum is great and we cannot do without it, but everything is changed once gravitational waves stepped into the room. Because now suddenly you have another way of looking at the universe, another way to gain information from the universe. Now, waves. Let's just think about waves for a second. Waves. We all have been to the pool. I am not nearly as proficient at swimming as I would like to, but I like to dip my hands in the pool, create little waves propagating out, or even if you drop pebbles into the water, you will see waves propagating out. Maybe some of them will interact with each other and form different patterns. Gravitational waves are literal ripples in the fabric of space-time, caused by heavy objects. And that changes depending on how heavy that object is. So here, say this is your space-time, and you have 3 different objects, 3 different masses. The heavier one is going to cause the most sagging, so to say, or warping, distortion of space-time. Smaller ones, not as much. And depending on how they are interacting with each other, you can get these ripples. You can get these ripples propagating over distances, over very large distances, which is good for us because we can hope to see them. And one of my favorite ways to do this is by thinking of how I can recreate that. Unfortunately, I can't do this. I can't make neutron stars collide or supermassive black holes collide, but I can observe them because those are the main ways in which we can get these kind of gravitational waves. Highly energetic events that are happening. So we either have to have supermassive black holes that are colliding, or stellar mass black holes that are colliding, maybe a supernova, or neutron stars that are colliding. And in all of these events, because you have these massive objects that are going around each other and they're distorting space-time, that starts propagating further and further and further away. And this is something that you can do, you can see literally happening if you have spandex, maybe a few people to hold the spandex, a drill bit, and 2 small balls, like this. If it plays. Oh. What gravitational waves are. You see those waves propagating. And let me do this in slow-mo, the next one. That is how gravitational waves would look if you had two objects which are almost the same size and they're going around in the fabric of space-time. And as you can see, this is a YouTube video, so I had to do it as well. So at Elon University, we build this. So big thank you to my co-professors up there who helped me do this. And that's me right there. And I'm trying that out as well. My fabric, literally, spandex of space-time. Oh yeah, let's call that spandex of space-time. And I created gravitational waves in the spandex of space-time. So that was fun. But let's do it in a scientific way. Let's have a simulation of two black holes. This isn't just space-time, but this is just the distortion of space-time. Let's see what happens when these two black holes, remember the supermassive black holes, merge galaxies, they're going around each other, they're going around, they're getting closer, and eventually they will combine and form one more massive supermassive black hole. And eventually it'll nicely stabilize itself. And that is what we are looking for. We are looking for gravitational waves that are released during this process. We have the two black holes that are going around each other, in spiral, going around, and eventually they collide. And at that merger, you see that little spike. That is the signal that gravitational wave detectors are looking for. But how do they physically do it? Now, these frequencies are tiny, very, very tiny. In fact, the observatories that they have built for this, in Livingston, for instance, the two arms that they have for the observatory are about 4 kilometers long. What's that in miles? About 2.5, 3-ish miles is about 4 kilometers. That's how long they are. But the science behind it is fascinating. You have your signal that starts off, and you have a beam splitter that is splitting the beams. They go to both the ends. But if there's distortion in space-time, those two beams are not going to stay the same. They're going to do this little dance. And because of that, when you have your light beam reflecting off of one end, and you have the other arm, which is reflecting light from the other end, the setup is so that if there is no distortion, those two beams cancel each other out, so you see nothing. But if there are gravitational waves that are passing through this observatory, now the two arms are no longer exactly the same. So now, instead of not getting any signal, you might get a little beep. You might get a little faint signal, depending on those gravitational waves. And that is how they detect it. And I'm hoping my sound is working on the computer, because let's hear them. Frequencies can be converted to sound. So maybe that's chirp. That's a detection. That is a gravitational wave signature that was determined by LIGO. And that's the observatory that we use. So that's the one on the very left here. That's LIGO. That's the LIGO observatory that has now found out these signals from the merger of stellar mass black holes. Now that's the important thing. They can find out the frequencies from stellar mass black holes or neutron star mergers, but the frequencies of gravitational waves that are coming from supermassive black holes lie out of the range of what LIGO can do. And that is where I come in. That is where I come in and I say, okay, if LIGO can't do that, and we are still waiting on LISA, PTAs can do that. They're working on it. They're working on confirmation of some. But what if we look at visual counterparts of these? So we see what's happening at the current observations that we have. So this is just a list of observations as of 2021. In the last 3 years, they've had a lot more. So imagine this little wing shape, but more. But we want to go one step further. We want to see what happens with supermassive black hole binary merger. And imagine this. Imagine you have two supermassive black holes right there. On the right, you have two black holes going around. And this is a three-dimensional projection of what the gravitational waves look like. So here, if you notice, it starts off evenish, but then one of those blobs is going to be bigger than the other. What happens is because it's uneven, but you need conservation of momentum. The merged black hole now gets a kick. It's the same concept as firing a gun. If you're firing a gun, the gun recoils back. That's the same thing that is happening here. It gets a recoil kick, causing that central black hole to now oscillate back and forth in the gravitational potential of this galaxy for about 1 billion years, which is great because it gives us a long window to be able to observe this. Starts off with big oscillations. Let's go back to our dragon, not dinosaur, dragon. The dragon has started to move, but then it gets tired and then it settles down back in the center of the merged galaxy. So that's exactly what's happening here. But in what I call phase 2, which lasts for about 1 billion years, it is still going back and forth in the center of this galaxy. But instead of being in the center, now you might expect to find this not exactly at the center, but displaced a little bit from the center of the galaxy. And that is the question. That is the question that I'm trying to answer. We know that supermassive black holes exist at the centers of basically all galaxies. Galaxies merge everywhere in the universe. Their two supermassive black holes start going around and eventually merge. This merger has a lot of gravitational waves that are emitted during the merger, which gives the black hole a kick. Can you observe these kicks? Can you observe a gravitationally recoiling supermassive black hole? Now, will you be able to observe this black hole as a black hole? It's moving, but there are lots of different parts to a black hole. You have the central region, you have the accretion disk, you have the torus, you have narrow line region, the broad line region, the jet. But does all of it stay with the black hole once it gets the kick? Not necessarily. The central region, up to about this little red circle, that's approximately what stays with the black hole. But the accretion disk does, which means even though it is moving, it is still accreting mass, and you can still observe it as an active galactic nucleus. Good for me, because that's what I'm using to observe. But you can have two kinds of observations that you can do. The first, you can have a velocity offset. So you have the things that are moving and the things that are left behind. And if you can find out the velocities using spectral analysis, you can see if there is a difference in the two velocities. I am more interested in the second kind, which is a literal visual offset between the position of the center of the galaxy and the position of the black hole. And if I can find that, well, then there's my candidate there for finding a supermassive black hole. So I started with about 100 different galaxies, which I visually inspected to make my sample. Actually, I started with 300 and then I went down to 100 galaxies. Visually inspected about 300 galaxies, and I decided, this is my own categorization of the galaxies, I decided I was going to look at galaxies that are smooth or smooth-ish. So no merging galaxies or galaxies that have a really dominant point source, because in these cases, I could either not tell exactly where the black hole is, or the black hole was so bright, I could tell nothing about the galaxy. I want to tell something about the galaxy. So I chose those first two. And going with those, I had a sample of about 100 galaxies. And I did two things to find if there was an offset. So coming down to the basics of what I did, assume that this is an elliptical galaxy that's in my sample. I had isophotes that I fit to the galaxy. So each ellipse represents an ellipse where the brightness of the galaxy, the intensity of light is the same. So I fit ellipses to this galaxy and found out a weighted mean of where the center of light of the galaxy will be. So I'm just analyzing visually what this galaxy looks like, analyzing the light, and then finding out where the center is. And then, this was the important part, I used the same image to find out where the black hole is. Is it there? Or is it somewhere else? And then I compared the two. I compared where the center of the galaxy is, and I compared where the black hole is. Are they close together? Are they overlapping? Or is there an offset? And here's an example of what I did. So here we have my wonderful galaxy 3C076.1. Names are so fun in astronomy. And on top there is my part 1, where I have the model of the galaxy. So each of those white rings, the white ellipses, they represent an isophot. And on the right is just original minus the model to make sure I did my job. I think that's all right. And I used all of those models to find out where the center of the galaxy was. And on the bottom is my part 2, where I took the same image, I smoothed it out, and then subtracted that from the original to find out if I can find a point source of light, which was that right there in the center, on the right, on the bottom. Now comes the time to compare. And now I'm like, okay, please, let me find something. Well, I'm standing here, so I did find something. So here we have the result of that particular galaxy. All of the little blue dots represent the center of each single ellipse. And that red star there, that represents the center of the galaxy. Thankfully, the green star is not close to the red star or really any of the little blue dots, which means that there is a difference. There is a difference between the position of the black hole and the center of the galaxy, which was great. I was thrilled. But my advisor said, wait, is this just a one-off? Can you find more? Sure. Okay, let's go. Let's find more. So this is the one that we just saw. Sorry, that is the one that we just saw on the right. One on the left is another image of the same galaxy, but in a different filter. This was NICMOS from HST. On the right is the white camera, again from HST as well. Both of them are visual images. I found a similar offset in the second one. Multi-filter analysis is great for confirming something that you are trying to find. But now the question is, they do kind of sort of look like they're similar offsets. Of course, the pixel scales are different because these are different cameras that we're looking at. Let's put them on a common scale to find out if they make sense. Thankfully, they did, for the most part. There is a little bit of a difference between these two. That's another galaxy that I put on there for comparison for another one that I found kind of sort of an offset with. But the reason why there is a difference between these two is because this particular galaxy does have a little dust lane in the center. So if you have just a visual image, that dust lane may obscure the black hole a little bit. In the infrared, I have a smaller displacement. It's still in the same direction, so that's a good sign. But that is why you need multi-filter analysis. A lot of you have probably used different filters to find out photography or even science, for those of you who are doing science and photography all together. But multi-filter is great because you get more information. More information is always good. And I got some more information from Hubble Space Telescope for a couple other objects. So I just wanted to show these two. These two were two new galaxies that we looked at with Hubble as well. And this was in cycle 25. So that was really exciting to get some new data from the Hubble Space Telescope. But let's go back to a galaxy that I talked about at the beginning, M87. We've all seen M87, the picture on the right. M87 has a displaced black hole. M87 here, the galaxy center and the black hole, they are not in the exact same spot, which is wonderful. It's like the big galaxy is supporting our claim of these recoiled black holes. But there is a small caveat. This displacement is approximately in the same direction as the jet, and that raises the question. Gravitational recoil, is that the only way you can get such displacements, or are there other ways? Turns out there are other ways. You can have something like M87, you can have a very powerful jet that is causing that black hole to move over time ever so slightly, but enough that it shows up as a displacement. The powerful jet, absolutely, that could be a way for this kind of a spatial offset. Or maybe you have a stalled binary black hole at the center. If you see a dual black hole, maybe there could be one of two things. Maybe it's just stalled, or it just hasn't gone and combined just yet. Or you could have some massive perturbers at the center of the galaxy. You could have globular clusters, you could have giant molecular clouds, and they are disturbing where exactly that black hole is. Of course, I'm hoping for the last one, gravitational recoil. That's what I wish all of these are, but we cannot rule out all of the others before doing analysis. So going back to the 100 galaxies that I looked at, I did get some robust candidates. I had about 6 robust recoil candidates, but 2 of them had their displacements, including the one that I showed you before, the 3C076.1. That displacement is great, but it's in the direction of the jet. So maybe the jet contributed. It doesn't refute gravitational recoil, but you do have to consider everything. So you could take observations, you could take velocity measurements that would confirm gravitational recoil, but for now, this is what we have. But in addition, I also found 3 others, which were looking like they could be candidates for dual AGN. I call these little dumbbell structures. 2 of these were found before. 2 of these were also discussed by others in other papers as potential dual AGN. So they're really close, but they haven't merged yet. And then there was one that hasn't been found yet, or hasn't been confirmed yet. So I was happy about this one. New contribution to potential candidates in the future. And that's where we are. This leaves us with some fun future prospects. We've LISA that's coming up that maybe our monster will fly to. Maybe LISA might discover some. And the results from this study will form empirical data points for LISA in the future. It also helps the claims with LIGO, of course. And getting access to James Webb Space Telescope with infrared. Oh, I'm itching to get my hands on some of the data and find out more about these monsters that are on the move. Thank you. Right. Sure. So stalled black holes is a theory where, as I mentioned, if you have 2 galaxies that are merging, you have 2 supermassive black holes that go around in a binary eventually and merge. There is a theory out there that what if it never gets close enough that the merger happens? What if it stops? What if at about 100 light years or so, it stops losing any energy that it can go closer and closer together? So what's happening at the centers of these galaxies when the black hole is merging is that is interacting first with everything else that's in the center, and you have what we call the 3-body problem. So you have 3 things, one of them is thrown out, the other 2 get closer and closer together. So one of the theories is, what if it just stops? What if there isn't enough material in the center to drive this kind of a merger? But we are hoping that it does. But it's a theory, yes. That's what a stalled binary black hole is. 2 black holes that just haven't been able to take that final step. I don't know the complete answer to this, but with LIGO, we are detecting the magnitude of the frequency. So we are detecting frequencies there. So we aren't detecting distance to the black hole, but the frequencies. There, if we work together with multiple observatories, we have at least 2 that are online right now. So that really narrows down and tells them where to look for. If you have a third one online, then that will triangulate the position even further. So that's actually a really good question. That is something that I'm still trying to answer, what the displacement tells us. And depending on exactly how much that displacement is, that could tell us, one, about how strong the recoil was. If we have velocities as well, that could also tell, okay, maybe how strong the recoil was. Do we find it very far away? Do we find it really just close to the galaxy? And that goes into some of the other displacement mechanisms and goes into, are they affecting this kind of a distance as well? So there are lots of things that the distance can tell us. And eventually, getting a statistical analysis of this distance can help us predict what we should or shouldn't see in the future in terms of, say, galaxy merger rates. Like, are you seeing more or less even number of displacements? Does that mean you have the correct number of galaxies, or how many galaxies are merging for a unit of time or not? Lots of things that we can cover.
Is it even possible to Doppler studies spectral lines at all, or even Doppler shifts? And are they consistent?
So when you say Doppler shift, you mean velocity offsets? Yes, absolutely. So that is the one method that I didn't do. That's the other observational method that you can do. So you can do a velocity offset measurement of these. So you get the spectra of these galaxies, and you have what we call the broad line region and the narrow line region, which are literally the broad line and the narrow line. And then you can see if there is an offset between those two regions, between the center points of those two regions. And if there is, that means one part of that black hole is moving faster or slower as compared to the other part. So those kind of studies are absolutely possible. And there are some people who have done those studies too. That's the next step. It hasn't been on the same galaxies yet, but that is absolutely the next step to confirm.
Okay, well, let's thank our speakers.
Thank you.